Ion electron configuration and periodic trends, lecture number 4. So in the last lecture we took those quantum numbers, the result of those solving the Schrodinger equations, give us places where we have electrons, and we expanded that between a single electron and over all the electrons in the atom to make these electron configurations. Right? So now we're going to then stop looking at individual atom, and we're going to talk about all the atoms in the periodic table and some trends that they have as a whole. And so we're going to start by looking at these ionic or ion electron configurations. So let's first review this concept of valence electrons. So we have two different types of electrons. We have those ones that are in the inside, close to the nucleus, the core electrons. We can abbreviate the core electrons in the electron configuration by those that have this same as the noble gas, that noble gas core. And then we have those outer electrons, what we call a valence electrons. Right? So those inner electrons are going to what we call shield those outer electrons, and we'll talk more about this shielding in a while. But but those valence electrons are the ones that are going to be involved in the bonding and the chemistry that we do. So when we talk about making ions, remember ions, the gaining or losing of electrons, it's those valence electrons, those outside electrons, that we're going to gain or lose. Right? If we're making a cation, right, to lose electrons, we see that that electron comes from that outside. So for sodium, for example, we have that 1s, that 3s, excuse me, electron. There's one of them. If it loses, right, now we have a completely filled sort of shell. Right, that then 2s is completely filled. So that's going to be a hazard. So it's going to be a +1. You can see the same thing is going to happen with calcium, where we lose the 2 electrons, we go to this noble gas electron configuration, or the aluminum, we go to the 3+. Right? Both of these we're going to a completely filled energy level, right, which is going to be more stable. And it's also easier to do than finding electrons to fill that 3 shell level. Conversely, if we look at these anions where they're gaining electrons, these negative electrons, they're also in an effort to gain and completely fill this outer level. And remember, for the periodic table, those ones that are formed anions are typically closer to having filled. So if we look at fluorine, for example, we're 1 electron away from completely filling that principal quantum number 2 shell. Right? So we can steal an electron from somebody else and get that completely filled outer shell when it makes a negative. Right? So these cations are always giving up electrons to form positive. Those electrons are going from this outer valence electron to the noble gas core. In the anion, we're gaining some electrons to again completely fill this outside, or having the same electron configuration as these very stable noble gases. When we do this, we see that a lot of the times we can get ions that have a similar electron configuration, what we call isoelectronic. It's ion or atom that have the same number of electrons, therefore the same electron configuration. Right? So if we look at these 5 that are isoelectronic with neon, we can have sodium plus, aluminum 3+, fluorine minus, oxygen 2-, nitrogen 3-. All of them are going to get to a case where they have the same electron configuration as neon. That's what isoelectronic means. The same number of electrons, therefore the same approximate ground state electron configuration. So far we've talked about the 2 sort of ends, the cation ones, the alkali metal, alkali earth metals, and then those halogens and those other ones on the other side where they're close to having either having that filled electron configuration. What we sort of ignored is this situation in the middle with the transition metals. Right? And we see, because of the way, once we fill those electrons and the repulsions that they have, that once we put electrons into those d orbitals, which are higher in energy than the s, once we put electrons in both of those, we see that they actually switch places. The energy levels change, which means now this s orbital is higher in energy. So if we're going to remove electrons out of that atom, it's going to come from the highest energy level, these s orbitals. So for the transition metals, we always see that the electrons come out of the s orbital first, and then the underlying d's. Right? Also remember that we have a sort of stability from either a completely filled orbital or a partially filled orbital. So sometimes we're going to get rearrangements of electron configurations so that we either completely fill one orbital or half fill two orbitals. And we'll look at the case of iron 2+ later. But if we look at iron 3+, the electron configuration for iron is that same as Ar plus 4s2 3d6. So if it's going to a 3+, it's going to lose 3 electrons. The first 2 that come out are from that 4s orbital. The last one comes out of the d. Right? So the electron configuration for iron 3+ is Ar 3d5, where we've lost those s electrons. We can do something similar for manganese here. When we go to a 2+, those first 2 electrons come out of this s orbital. If we look at the iron 2+, for example, though, if we took 2 electrons away from that, we would think we would go to Ar 3d6, where we have now no s electrons and then 6 electrons in the d. But we can see if we take one of those d electrons and promote it back into the s, now we have a half-filled s orbital and a half-filled d orbital, which is more stable than the other arrangement. So for the iron 2+, the electron configuration that we would get, if you can see it, would be Ar 4s1 3d5. Because of this special arrangement with these half-filled orbitals are being more stable than non-filled orbitals. So we always want to either go completely filled or half-filled. If you remember the Hund's rule that says that the more stable configuration is the one where we have the most parallel spins. In these orbital situations, that's why these are more stable. Right? We have all of those being half-filled. The spins are more parallel. We get the maximum number of parallel spins. We get some special stability. So let's take a little bit of time and talk about what happens when we remove electrons or interact these. So we're talking about the interaction between these valence electrons on the outside and those inner core electrons. And we're going to use a property we call the effective nuclear charge, or Z effective, which is the positive pull from that nucleus that those outer electrons feel. So the greater the Z effective, the stronger these outside electrons are being pulled towards that nucleus. Right? And the Z effective can be approximated by taking the atomic number Z minus some shielding constant. And we can approximate the shielding constant by being that value being the same as the number of core electrons, or the noble gas that comes before that atom. So Z effective can be approximated as the Z, the atomic number, minus the number of core electrons, or the number of protons in that noble gas that comes immediately preceding that species in question. So if we look here in this table, we see sodium, magnesium, aluminum, silicon all have a greater increasing number of atomic number. We go 11, 12, 13, 14. But they all have the same core. They have the same noble gas core, right? 10. So as we see, as we go across this periodic table, right, from sodium to magnesium, the Z effective increases. And we can see the resulting effect on the radius that Z effective has. So if this Z effective, the amount of pull those outer electrons are having is greater, we're going to essentially suck those electrons in. So the larger the Z effective, the closer those electrons are going to be pulled. So as we go across the periodic table, we see that the radius, the size of the atom, actually gets smaller. Right? Remember, those electrons are all starting out at approximately the same distance, but we have a larger positive pull on those, that's pulling them down. So we can also think of this is Coulomb's law, that the attraction between two charged particles is going to be a effect of both the magnitude of those charge and the distance between those. Right? So we see the effect of magnitude as we look across the periodic table. The magnitude of those charges increases, so we get a stronger Z effective. We can see the effect of this distance by looking up and down the periodic table. As we go further away, those outside electrons are getting further from those positive protons. They're essentially feeling less of them. So as we come closer together, they get larger. So Z effective essentially increases going up the periodic table and from left to right. Right? Or we can think of it as the horizontal in this direction. So we can look at that. We've seen its sort of effect across the periodic table on radius. We can extend that then to going down the periodic table. Now, as we go down the periodic table, we're getting more and more electrons. Our principal quantum number of those valence electrons is increasing, which means they're getting bigger. So we see that the atomic radius increases as we go down the periodic table because of this just increased mass. We're just continually adding more and more electrons. And it increases across the periodic table from right to left because of this decrease in the Z effective. So in general, we see the opposite trend in ionic radius. And we can see this if we graphed all of the atomic radii. We see that always we have the smallest value for those halogens, or most of the time. The largest ones, if we go across, are going to be those alkali metals. And for the most part, we see this general trend. But we see this very loopiness. Those are those transition metals that we're having some. We're increasing the amount of electrons, but we're not really changing the distance. So for the transition metals, we see a sort of a difference in this general trend. If we look then at these radii as we move from the neutral atom to the charged, right? If the Z effective is the effect of those electrons by pull towards this positive nucleus, if we increase the number of electrons, right, out here on this outside, compared to the number of protons, we're going to see that that pull is going to be decreased. So those anions are actually larger than the normal atomic radius. So if we add electrons, we see that the size actually gets bigger. Conversely, if we took away the electrons outside compared to the protons, we see that now the positive is going to outweigh those negatives, and each electron that's left is going to feel a larger pull of this positive nucleus, and it's going to shrink. So we can see that here graphically, that as we take electrons away, the atomic radius or the ionic radius gets smaller than the normal. Right? And we see that, so in general, cations are always smaller than the atom from which they're formed, and anions are always larger than the atoms they form. So the magnitude also has an effect. A 2 plus is going to be bigger than typically a 1 plus. A 2 minus is going to, or excuse me, the other way around. 2 plus is going to be smaller than a 1 plus, typically. Anions, the 2 minus is going to be bigger than a 1 minus, because that Z effective is having a larger effect. Okay. Let's look at a couple other general trends. We've talked about moving and adding electrons. Let's see what happens to the energy associated with those changes as we go across. The first one we're going to talk about is this ionization energy. It's the minimum energy required to remove an electron from a gaseous atom in its ground state. So we can see the first ionization, this I1, is going to be taking that neutral atom and removing an electron. The second ionization is going to be taking an electron from that positively charged species to form a 2 plus ion, and so on. So this is a successive removal when we go across these ionizations. And in general, because of this Z effective, the first ionization is always going to be less than the second ionization, which is going to be less than the third. Right? Because now as we move electrons, we get that Z effective becomes stronger, it's harder to remove more electrons. So if the Z effective is playing an effect of how easy it is to pluck these out, our periodic trend is going to follow or mirror that Z effective. We're going to see that it's going to be the highest where we have the largest Z effective, and it's going to be the lowest where we have the smallest Z effective. So we can see across, if we go from the filled, this noble gas core, we see in general that as we go down the periodic table, we get a decrease in this first ionization energy. As we go across the periodic table, we see a general increase. So we can talk about the general trend for first ionization increases up the periodic table, and again from left to right. If we look at the opposite, this electron affinity, this is the negative energy of when we pull an electron out of, or put another electron, into that atom in the gas state. So we can take some general atom X here, add an electron to it to form the anion. We can see that if we do it for fluorine, we add that energy, we get the delta H, the energy change for this is a negative 328. Electron affinity is always talked about the negative of that, so we talk about the electron affinity of this process being a plus 328. For oxygen, again, the delta H is a negative 141, so we see the electron affinity is a positive 141. So in general, we can talk about these electron affinities increasing the same way. That as we go across the periodic table from left to right, we see a general increase in these electron affinities, either becoming more negative or the negative becoming more positive. They're just a larger magnitude as we go in that direction. As we come down, generally we see a smaller value. So the lowest ones are going to have a smaller value than the upper ones. We can trace this back to the Z effective as well, because if we have a small positive by adding one more electron where we have all these other electrons, it's not going to make as big a difference as when we have the electrons very close together, very close to this positive charge, where we add one. It's going to be much easier and much more favored process. Okay. So then we will expand on this and then start talking about actually forming bonds between two atoms in the next lecture.
I don't get